Artificial intelligence systems are routinely deployed to the public long before their systemic impacts are fully understood today. We have seen this pattern of releasing unregulated technology before. In the late 1950s, the pharmaceutical industry operated under a similar deploy-first mentality. The sedative thalidomide was aggressively marketed to pregnant women to alleviate morning sickness. It was released with inadequate testing for its effects on fetal development, and manufacturers delayed their response even after reports of severe harm emerged. The resulting catastrophic birth defects across multiple countries forced the creation of the modern FDA safety and efficacy standards we rely on today. The AI industry is currently operating in its own pre-FDA era. By rushing algorithms to market, developers shift the burden of algorithmic risk directly onto the end user. This risk is compounded by a modern data paradox. Traditional anonymization, simply stripping out names or ID numbers, is mathematically insufficient when dealing with big data. Big data refers to extremely large datasets that may be analyzed computationally to reveal patterns, trends, and associations. The 2017 Strava heat map controversy illustrates this exact aggregation risk. The fitness app aggregated a massive dataset, plotting over 3 trillion individual GPS coordinates collected from anonymous users' wearable trackers all over the world. By illuminating the most frequently run routes, these seemingly benign data points inadvertently outlined the exact patrol paths and layouts of high-security installations, like the HMNB Clyde nuclear submarine base. When enough benign data points are aggregated, mathematical overlapping destroys anonymity. The sheer volume of inputs allows an observer to accurately triangulate highly sensitive information. This aggregation goes beyond geographic location into individual behavioral inference. Over a decade ago, the retailer Target applied predictive analytics to consumer habits, assigning shoppers a pregnancy prediction score. They strictly reflect the statistical distributions of the data they are trained on. We can see exactly where human prejudice enters the system by looking at the 5-stage pipeline. This workflow moves from data collection and labeling, through feature selection and training, and finally to deployment. The first vulnerability occurs immediately at data collection. Facial recognition models provide the clearest failure case here, as unbalanced demographic inputs funnel directly into the system architecture. The MIT Gender Shade study quantified this failure. It revealed that commercial facial analysis systems achieved a 99% accuracy rate for white males, but dropped to a 65% accuracy rate for darker-skinned females. A model trained on an unrepresentative demographic dataset is not malfunctioning. It is performing exactly as engineered by accurately reproducing a biased sample. In natural language processing, or NLP, the branch of AI that interprets and generates human language, societal bias is transmitted through a specific mathematical mechanism called word embeddings. This method plots individual words as data points on a spatial grid, calculating their statistical relationships. The model learns relationships based on how closely words appear together in the training text. This means if you take the mathematical vector for woman, add doctor, and subtract man, a biased model resolves the equation to equal nurse. This theoretical math had direct consequences for Amazon's automated AI hiring tool. The company trained its model to vet applicants using 10 years of historical resumes, which came predominantly from men. Because the algorithm learned to associate successful technical candidates with male language patterns, it systematically downgraded female applicants. It actively penalized resumes that contained terms like women's chess club. Amazon ultimately scrapped the project. The bias was embedded so deeply into the mathematical weights that it could not be cleanly patched out of the system. When historical social inequities are fed into the feature selection stage, the algorithm codifies discrimination as a statistical ground truth. The compounding effect happens at the final pipeline stage, deployment. This introduces the systemic danger of the algorithmic feedback loop. Predictive policing is the textbook example of a deployed feedback loop in action. The operational mechanics are straightforward. If an algorithm incorrectly predicts high crime in a specific neighborhood based on historical bias, a heavier police presence is dispatched. That increased surveillance inevitably results in more arrests in that specific area. Those new arrest records are then fed directly back into the model's training data. This creates a self-fulfilling prophecy, artificially confirming the algorithm's initial biased prediction. Without rigorous mathematical constraints, deployed machine learning models scale historical bias exponentially across the population they govern. The unified mathematical reality of AI operates in stark contrast to our highly fragmented legal response. Current regulatory frameworks struggle to govern modern data collection. Europe takes a strict, centralized approach under the GDPR. This framework mandates specific technical constraints, enforcing concepts like data minimization, collecting only what is strictly necessary, and strict storage limitations. The United States, however, relies on sector-specific protections. For medical records, this means relying on HIPAA, which is built on pillars of patient confidentiality, data security, and strict sharing standards. This creates immediate compliance friction in the U.S. The absence of a unified federal standard has resulted in a complex state-by-state legislative patchwork, with different rules applying as soon as data crosses a border. Navigating this fragmented regulatory map makes deploying a national, data-hungry AI system a massive legal and operational liability. Sector-specific laws like HIPAA also contain a critical loophole. They strictly govern healthcare providers, but they fail to protect against third-party data collection by independent apps or data brokers. We saw this exploited when data brokers legally harvested and sold the location data of people visiting abortion clinics. Highly sensitive medical context was monetized entirely outside of HIPAA's jurisdiction. This vulnerability to third-party data harvesting collides with the memory risks inherent to large language models, or LLMs. LLMs are auto-encoding systems, neural networks that learn how to represent data by masking parts of an input and predicting the missing pieces. To achieve this, they are trained on hundreds of gigabytes of uncurated, scraped internet text. This exposes the foundational danger. Unlike previous algorithms that only generalize statistical patterns, LLM architectures inherently risk memorizing and regurgitating explicit, sensitive information directly from their training data. A 2025 study evaluated data masking against an LLM's ability to extract hidden data. Standard masking hit a hard ceiling, hiding identities only 42.9% of the time. But through contextual inference, LLMs bypassed masking entirely, leaking social security numbers at a 100% rate. This brings us back to the core lesson of the thalidomide tragedy. You cannot build trust, fairness, or privacy into a system as an afterthought once it has already been deployed. Ethics is not a philosophical debate. It is an engineering parameter. If we want privacy and fairness in our artificial intelligence, those protections must be mathematically constrained at the foundational architecture level.